This talk is about logarithms and exponentials. So what are logarithms and how did they arise? What are exponential growth and the exponential number e? And what's the connection between these topics? Around the year 1500, Nicolas Chouquet of France and Michael Stiefel of Germany showed how to turn certain calculations involving multiplications and divisions into simpler ones with additions and subtractions. For example, look at this table of the first few powers of 2, where, for example, 2 to the power 5 is 32 and 2 to the power 7 is 128. As they noted, to multiply powers of 2, we just add their exponents. So to multiply 32 and 128, we write this product as 2 to the 5 times 2 to the 7, which is 2 to the power 5 plus 7, or 2 to the 12, which from the table is 4096. Let's now rewrite the equation x equals 2 to the n as log to the base 2 of x is n. Then the log to the base 2 of 32 is 5, the log of 128 is 7, the log of 4096 is 12, and so the log of 32 times 128 is the log of 4096, which is 12. But this is 5 plus 7, which is the log of 32 plus the log of 128. And in general, for any two numbers a and b, the log to the base 2 of the product a times b is just the log to the base 2 of a plus the log to the base 2 of b. And similarly, if instead of the powers of 2, we'd started with the powers of a number capital N, we'd get a similar result shown here for logs to the base n. In the early 1600s, when advances in astronomy and navigation required much calculation, the ability to turn multiplication sums into addition ones became increasingly desirable. So in 1614, John Napier of Edinburgh produced his description of the wonderful canon of logarithms, containing excellent brief rules, as he called them, for simplifying such calculations. Napier considered 2 points moving along straight lines, with the upper line being of finite length and the lower one of infinite length. At each stage, the upper point moves so that its speed is proportional to the distance that it still has to travel, so it's slowing down, while the lower point, representing its logarithm, forever travels at constant speed. It follows that, as his numbers increase, Napier's logarithms decrease. But his definition gives us nearly the result we want. For any numbers a and b, the logarithm of a times b was log of a plus log of b, but he then had to subtract the number log of 1, which, for the scale he used, is the awkward number shown here. This awkwardness was soon removed by Henry Briggs, the first professor of geometry at Gresham College in London and at Oxford University. On seeing Napier's book, he exclaimed, "I never saw a book which pleased me better or made me more wonder," but then added, "It would be much more convenient that 0 should be kept for the logarithm of the whole sign, that is, that the logarithm of 1 should be 0. Briggs visited Napier in Edinburgh, where they first spent many minutes beholding each other in admiration without speaking a word. But the result was Briggs's logarithms to base 10, in which log of 1 is 0, log of 10 is 1, log of 100 is 2, and so on. And if x equals 10 to the n, then log to the base 10 of x equals n. And where the logarithm of a times b is now simply the logarithm of a plus the logarithm of b. On the right are a few of his logarithms, all calculated painstakingly by hand to 14 decimal places. Let's now turn to our other topic, exponentials. To illustrate what's meant by exponential growth, here's a story about the invention of the game of chess. The wealthy king of a certain country was so impressed by this new game that he offered to the wise man who invented it any reward he wished. To which the wise man replied, "My prize is for you to give me 1 grain of wheat for the first square of the chessboard, 2 grains for the second square, 4 grains for the third square, and so on, doubling the number of grains on each successive square until the chessboard is filled." The king was amazed to be asked for such a tiny reward, or so he believed, until his treasurers calculated the total number of grains of wheat. This works out at just under 2 to the power 64 grains, enough wheat to form a pile the size of Mount Everest. Placed end to end, these grains would reach to the nearest star, Alpha Centauri, and back again. Let's see how quickly other sequences can grow. A very simple form of growth is linear growth, as in the counting numbers n equals 1, 2, 3, 4, 5, etc. Somewhat faster is how their squares n squared grow. And even quicker are their cubes n cubed. These are all examples of polynomial growth, because they involve powers of n. Alternatively, we could look at powers of 2, or of any other number. In the chessboard story, the numbers 2 to the n, the powers of 2, quickly increased because each number is twice the previous one. And the powers of 3 grow even faster. These are examples of exponential growth, where n appears as the exponent. Let's compare these types of growth. Here are the running times of the polynomials n and n cubed, and of the exponentials 2 to the n and 3 to the n, when n is 10 and 50, for a computer doing 1,000,000 operations per second. When n is 10, all 4 of these take a fraction of a second to calculate. But when n is 50, the polynomials n and n cubed still take less than a second, while the exponential 2 to the n would take over 35 years, and the exponential 3 to the n would take 23 billion years. So in the long run, exponential growth tends to exceed polynomial growth, often by a huge margin. Algorithms that run in polynomial time are generally thought to be efficient, whereas those running in exponential time normally take much longer to implement and are regarded as inefficient. Let's now meet the exponential number e. What exactly is this number, and how did it arise? In 1683, the Swiss mathematician Jacob Bernoulli was calculating compound interest. Given a sum of money to invest at a given rate of interest, how fast does it grow? The answer depends on how often we calculate the interest. How much is earned if we calculate it yearly, or twice a year, or every month, every day, or continuously? As an example, to keep our calculations simple, let's see what happens if we invest £1 at the unlikely annual rate of 100%. After 1 year, our £1 doubles to £2. But if instead we calculate the interest twice a year, that's 50% each time, then after 6 months, our £1 is multiplied by 1.5 to give £1.50, and after another 6 months, that amount is multiplied by another 1.5 to give £2.25, which is greater than before. Next, let's calculate the interest every 3 months. Here there are 4 periods, and after each one, the amount is multiplied by 1 1/4. First to £1.25, then to about £1.56, then to £1.95, and by the end of the year to about £2.44, which is £1 times 1 1/4 to the power 4. And so the final amount is larger still. As the periods get shorter, what happens? Do these final amounts increase without bound, or do they approach a limiting value? The results are shown here to 5 decimal places. To find them, we note that if the year is divided into n periods, then after each period the amount is multiplied by 1 plus 1 over n, so that the final amount is 1 plus 1 over n, all to the power n. We also see from this table that as n increases, these final amounts approach a limiting value that corresponds to when the interest is calculated continuously. This limit of around 2.71828 is our exponential number e. Here's our exponential number e to 18 decimal places, and like the circle number pi, its decimal expansion goes on forever. It's an irrational number. The letter e was introduced around 1727 by the Swiss mathematician Leonhard Euler, and first appeared in print in 1736 in his Mechanica, a book on the mathematics of motion. It appears here in the penultimate line, where e denotes the number whose hyperbolic logarithm is 1. So is e also related to logarithms? Indeed, it was Euler who made the greatest advances in understanding exponentials, when he investigated e and the related exponential function y equals e to the power x. And in 1748, he collected many of his results from earlier works in his Introduction to the Analysis of Infinites, one of the most important mathematics books ever written. Let's now look at some of Euler's main findings. We've already seen that e is the limit of the numbers 1 plus 1 over n, all to the power n, as n increases indefinitely. And similarly, we can show that e to the power x is the limit of 1 plus x over n to the power n for any number x. But as Isaac Newton had already shown, e is also the sum of the infinite series shown here. Here the denominators are the factorials 1, 1 times 2, 1 times 2 times 3, and so on. And similarly, there's a series for e to the power x, which converges for every value of x. On the right is the graph of y equals e to the x. An important feature here is that at each point x, the slope of the graph is also e to the x. That is, the slope at any point is the y value. So the curve becomes ever steeper as x increases. Let's now look at logarithms to the base e. If y equals e to the x, then x is the logarithm of y. It follows that the logarithm of e to the x is simply x, and that e to the power of log y is just y. It also follows that if we take x, calculate e to the x, and then take its logarithm to base e, we get back to x. And similarly, taking e to the power log y brings us back to y. So these logarithms and exponentials are inverse to each other, with each undoing the other. Graphically, as we see on the right, this means that the graphs of e to the x and log x are reflections of each other in the line y equals x. Moreover, our logarithm law, log of ab is log of a plus log of b, and the exponential law, e to the x times e to the y equals e to the x plus y, turn out to be essentially the same result. For in the logarithm law, we write a equals e to the x, and b equals e to the y, we get log of e to the x times e to the y equals log of e to the x plus log of e to the y, which is just x plus y. Now take exponentials of both sides of this equation. This gives e to the x times e to the y equals e to the x plus y, which is the exponential law. To conclude, I'll return briefly to exponential growth for those familiar with calculus. In 1798, Thomas Malthus wrote his famous essay on population, where he contrasted the steady linear growth of food supplies with the exponential growth in population. He concluded that, however one may cope in the short term, exponential growth must win in the long term, and there'd be severe food shortages, as was borne out in practice. How fast do populations grow? If n of t is the population size at time t, and if the population grows at a fixed rate k, which is proportional to its size, then we have the differential equation dn by dt equals k times n. Rearranging this as dn over n equals k dt, we can integrate this to give log of n equals kt plus a constant, or, on taking exponentials, n of t equals c times e to the power kt, where c is another constant, which turns out to be the initial population of n0 marked on the graph. So we have exponential growth. And in the same way, we can model exponential decay, as for example, for the rate of decay of radium, or the cooling of a cup of tea. And with that, may I thank you for listening.